Initially, I was just reading this paper to for another paper I wanted to read, just to get an idea of what like the current like I know that rotary encodings are used a lot, but I just wanted to get an idea why. But after reading the paper, I'm very skeptical of this actually improving models. Um, so I'll show you why. But uh, like, it's still a cool method, but I want to show kind of why I'm skeptical of this working. Yeah, uh, I know that it's used a lot though, so I'm curious why. Anyways, this is called RoFormer, and it basically takes the positional encodings of a transformer and makes it it makes it both absolute and relative, and it does so in a way where the model doesn't have to learn these encodings itself, and they just put a prior on the model, and so the model doesn't have to learn it itself. And yeah, it's called RoFormer, and the paper came out like a year ago, and you see, like, if you look at Hugging Face, you'll see rotary positional embeddings everywhere. So yeah, let's just get into kind of how it works. So let me swap these. The normal, yellow. If you have seen any transformer model, you'll know that the inputs are a sequence. So you have a sequence such as I love cats, and each of the words are represented by an embedding vector of size, say, D, something like that. So you have, say, an S by D matrix, and that's how you represent your sequence. And then you throw this through a transformer, which is made up of self-attention blocks. And the thing with this sequence is it's actually not a sequence. It's an unordered set at first. So if you just have a bunch of tokens, it's an unordered set, and that's due to how self-attention works. And the way self-attention works is it's like a positionally it's positionally invariant. So if I have my attention matrix, and this is the vector I love and cats, and this is I love cats. If I don't have any positional prior, which I don't in a self attention that's plain without anything else. If I just have self attention, um, oh yeah, and I'm just gonna briefly go over self attention. Like I'm not gonna go into self attention in this video. So I made a video on transformers, and there's a lot of people who made a video on transformers. So I highly suggest you go check out a video on transformers before watching this one. But yeah, the assuming you know a little bit about self-attention, it makes this attention matrix. And if I were to swap out, say, love and cats in both these positions, it'll result in the same attention matrix, but with the position swapped. And that's just because you're just doing inner products, and an inner product, like the inner product between, say, love and I right here, it doesn't know anything about the other inner products at all, and it's not going to know anything about those because of the way that the attention matrix is just created. So there is no positional prior, and that's why in the attention is all you need paper, you know that they before these went through a transformer, it went through positional encodings. It went through some positional encoding layer, and then it went through the transformer. And the positional encodings are a way of adding positional information to the sequence. So the initial transformer added positional encodings by using sinusoidal embeddings. So the way they did that was by having, let me split this up like this. So they had sine waves of varying frequencies. So say I have a sine wave here, like that. That's terrible. Like, I guess I can't draw. Okay, there we go, like that. And then I have one that's going even faster. So the frequency is even faster. And then you have another one where the frequency is even faster. And I'm not drawing the rest, but you have this one would be even faster and even faster. So the frequency is higher and higher for each of these sinusoidal embeddings, which are formulated. The formula is right here, but you can visualize it like this. I'm not going to go into exactly why the formulation is the way it is like that, but you can visualize it like this. And what you do is for each token. So say our token is I. So our tokens are I, love, and cats. For each of these tokens, you kind of sample the sine waves of varying frequency along a like along all of the for every single sine wave. So notice how this one is like high in the first wave, it's kind of mid in the second wave, and it's low in the third. And then love would sample it somewhere else, and it's also high here. It's also mid here, but it's very high here. And I guess if I were a transformer and I were looking at this, I would be like, oh, the this freak or the waves here and here, they're very close, and uh, in this space or in this frequency, it's not. They're far apart, so maybe these two words are close together. But I mean, I didn't draw this to scale, but that's kind of how it can reason. It can say, oh, these the waves in this the waves in this dimension are similar, while the waves in the third dimension are different. So they may be close to each other. While if the value in each of the dimensions is very different, then you can say, oh, maybe the words are very far apart. And you basically have this sine a different wave for each dimension. So if our dimension is of shape D, then you would have D different sine waves, and yeah, and you just sample them, and that's absolute. So and it's absolute because it just like if you if you visualize it, you can kind of see that like this word knows exactly where it is in the sequence compared to this word, which knows exactly where it is in the sequence. And the only problem with this is, what if you have like repeating waves, and this doesn't happen for I think it's 10,000 values, which is way too much for this to be repeating. It's like an attention matrix that big isn't, it's not going to be a problem, and if so, you can scale the matrix, and it's not a big deal until you actually get repeating values. So they're independent, or they're yeah, you're not going to get repeating values. So that's absolute positional encodings. Now there's some problems with them. Um, The first problem is they're only added to the input. So if I have this input I love cats, you add them right here. And then in the transformer, they're not added again. So if in a transformer you have your sequence here, you add the positional encodings. So you send those through, you add the positional encodings, and then you send this through the first transform block. And then you send that through another transformer block. And again, you keep sending this through a bunch of transformer blocks. And if this transformer block wants to treat this as a sequence as opposed to treating it as a unordered set, then it needs to carry, then the previous layers need to carry the positional information past each, like through themselves. And that's a little difficult because the model has to learn how to carry this positional information if it wants to model this positionally at a higher level in the transformer. You may be able to add positional information here, and that's kind of what they do in this paper. But I don't know if experiments have added this absolute positional information in the intermediate layers. Be interesting to see if that would help it out. But that's one of the problems. Like, it has to carry this positional information through, and that may cause it to run into some issues. Another problem is it's very bad at extrapolation. So if it's seen for all the positional information it's seen, it's very good at modeling that. But say our transformer only learned on 3 word sequences, then at a much later time, it's going to see this positional information it's never seen before, this positional vector it's never seen before. And since you're adding it directly to the encodings, it's going to have no idea how to, like, it may have an idea on how to deal with it, but since it didn't directly deal with it like it did over with these embeddings, it's going to have some issues. And that's what you see. You see that the transformer has, the original transformer has issues extrapolating. And that's partially why I was reading this paper for another paper that talks about how to extrapolate this information. This paper does not go into the extrapolation factor, but it's an important thing to bring up because it's a very prominent issue in transformers that they don't extrapolate well beyond sequences that they haven't learned, or sequence sizes. So that's absolute positional encodings right here. Now, they talk about relative positional encodings, and they go into a ton of different ones, and I didn't really, I looked at them and I'm like, let me just get to their approach. But there's a lot of approaches that try this before, and they say, well, they're not that good compared to theirs. So what, and kind of what you want in a, like, if we kind of formalize this as, say I have say I have an n by n matrix, which is our attention matrix, and the queries are going to be of shape, say, n by d, and the keys are going to be shape n by d, and you multiply those together to get your matrix, like so. And then this can be your queries, and this can be your keys. Now, whenever you're let's just look at how the positional information would look if we want this to be relative. So if you want this to be relative, then you want to model, say, like a relative position, which is r is equal to m minus n, where m is the location in the query and n is the location in the key. So in this case, it would be 0, 1, 2, 3, 4, 5, and 6. And same here, 0, 1, 2, 3, 4, 5, and 6, and this is our attention matrix. So if we look at the 5, not 6, 0, 1, 2, 3, 4, and 5, 0, 1, 2, 3, 4, and 5. So in this first, so along this diagonal, n minus, so this is our m and this is our n, m minus n is always going to be 0. And then if you go past the diagonal, you'll have, say, 0 minus 1, that's negative 1, so it'll be negative 1 along this diagonal, and then it would be negative 2 along this diagonal, and this would be 1 here. So you can kind of see that in this way it can kind of learn positional information, but also if we model it this way, it's kind of discrete, but I think it's a good way of like looking at how you can kind of get positional information. So if I'm, say, right, if I'm looking at this part right here, then, or if, yeah, this negative 2 tells the key where it is relative to the query, and where it is in the sequence, as opposed to generally where it is in the sequence as an absolute marker. It's relative to the position of the 0th vector, as opposed to where it is in the whole sequence. And that's what you want with relative embeddings. Where am I relative to another vector? So that's what this matrix represents. And the problem is this is a discrete representation and it's not normalized, so it's not going to do well if you just say add this matrix to it. But what they do is they model it using rotations, and they have there's an example here. So say we only have 2 dimensions. So we only have so our vectors, our queries would be of shape n by 2, and our keys would be of shape n by 2. Then it's easy to visualize 2 dimensions. It's difficult to visualize more than 3 dimensions. So we're just going to compress this down to 2 to kind of see how this this relative positional embedding works. Now, what you can do is if I have, say I have a vector, we'll say our matrix is, we'll say our queries and our keys are the same just to make this easy to visualize. So our queries is equal to keys is equal to a 1, we'll do 1, 1. So these are our queries and keys, 1, 1. And that just makes it easy for me to draw. So this is the vector representing our queries and keys. This would just be, and we'll call this first value x hat 1 and x hat 2. Now, what you do is you will rotate this, and let's say that we want to rotate it 90 degrees or so. So if you rotate this 90 degrees, so this is we'll say theta is equal to 90, then yeah, all right. So so if our queries and keys are both 1, 1, and let's say we have a sequence of size 2, so n is equal to 2, and let's say that is also 1, 1, then this would be our x1 and this would be our x2. So x1 is here is equal to x2. And yeah, that just makes it easy for me to draw. Then for x1, you rotate it 90 degrees. So we'll rotate this 90 degrees, and that'll bring it right here. So that's our 90-degree rotation, and this is x1 hat. So it's x1 rotated 90 degrees. And then what we do is we rotate x2 by 2 times 90 degrees. So it'd be 90 degrees times 2, 90 degrees times 2, because the index is 2. So you would rotate it here, and this would be x hat 2. Now you can kind of see where the relative information comes from. So maybe we have another vector, x3, and then that would be rotated again. And this would be, say, x3. And if all these are the same vector, say they're all I, say this vector x represents the word I, then if you just had if you didn't have positional information, then you can see it would just be the same vector. But adding the positional information makes it different vectors each, meaning that there is positional information added to this vector. Now this first vector, it can kind of, whenever you're doing, say, a dot product with something, you can kind of, if you do a normalized inner product with, say, a vector that was really close, like right, with this vector, x2, then you'll get 0 because they're perpendicular. So x1 inner product x2 would be 0. So that would be 0. But then x1 inner product x3 would be -1. And x1 dot product x1 would be 1. So you can see this relative, and you can see the relative information if we were to look at it in terms of x2. So if x2 were to do a dot product with x1, then yeah, I guess we can make a table. So this would be x1, x2, and x3. It's our dot product table. This is x1, x2, x3. So the dot product with itself would be 1, and the dot product of x2, x1 with x2 would be 0. The dot product of x2 with x3 would be 0, and the same here. And then these would be -1. x1 with x3 would be -1. x3 with x1 would be -1. And you can see this is the matrix we were looking for, except instead of 0 on the diagonal, it's a 1. And in 2 dimensions, this works well. And if you make theta smaller, then you still get a matrix that looks like this, and the information is probably better than zeros and -1s. But if I were to say make theta like, I don't know, like 1 degree, then it'll only rotate it a really small amount, but every new position will rotate it a little bit more. So, and if they were the same vector. And that's the basic idea of this. You do this for every layer, and you just rotate the vector a little bit, depending on where it is in the sequence. Now, the trick is you don't do this in 2 dimensions, you do this in n dimensions. So they have this matrix. Here's our rotation matrix for 2 dimensions. You've probably seen this before if you've taken a linear algebra class, the good old rotation matrix, but they generalize this to n dimensions where you can rotate a vector. So this is one vector in our sequence, one embedding representing some word. So this vector here is d-dimensional, and if you look at this matrix, it's kind of a lot to look at, but if you break it down, it's not too bad. So this matrix here is of shape, this is d by, what would that be? Oh yeah, d by d. D over, it's a d by d matrix. So d by d. And you can see in this first quadrant, there's the cosine and then the sine theta. This first quadrant here. Yeah, there's the sine, there's the cosine and sine theta, and the negative sine theta and the cosine theta. And then you can see there's a bunch of zeros. Now, what this does is it rotates the first 2 dimensions in. So whenever you multiply this by your weight matrix, WD minus 2, WD minus 1. Whenever you multiply this by your weight matrix, and since there's zeros everywhere else, I'll represent the zeros as blue, actually. Easier to look at, so zeros, 0, 0. So whenever you multiply these together, the only thing that's going to be affected is your W1 and W2, if we ignore the rest of this matrix for now. So just the first 2 rows and columns, then you'll rotate your first 2 values in your vector. So you can think about this as taking your vector and then taking the first 2 dimensions and then rotating it as we did up here. And you can see the way they rotate it is cosine sine m times theta, where theta is some constant and m is the location in the sequence. So in this case, this would be 0, and then this would be 1. Oh no. This is your vector representing. So this is, say, w sub m, where it's a vector in your sequence at position m. So m stays constant throughout this whole matrix, and theta stays constant throughout the entire sequence. So this is one vector in your sequence, and you multiply it by, and you do the dot product with this rotation matrix, and in the first 2 dimensions, it will rotate it by some constant amount multiplied by wherever it is in the sequence. So say this was say m is equal to 0, and our vector looked like this, then it would rotate it. It actually wouldn't rotate it at all if m was 0, I don't think. It would rotate it a small amount, if anything. I don't think it would rotate it at all, because the angle would be 0. And then if you have m is, say, equal to 1 or 2, then it would rotate it a little bit more, depending on what your theta is. And if m was very large, it would rotate it a lot. And then you do this for, and this is just for 2 dimensions. And then the next 2 dimensions, you do the same exact thing, independently of the first 2 dimensions. So notice how this part of the matrix right here only works on the next 2 parts, the next 2 parts of your vector, your d-dimensional vector representing one word. So this may represent like I or something. So you'll rotate those independently of the first 2 parts, independently of the first 2 parts of the vector. And you do that for all parts of the vector. So you just split it into pairs of 2, and you rotate it. So you can kind of see that here, where you split your word here into just 2 values. And then you rotate those 2 values by some amount. And then that's your new representation in that vector. And then you do that. You do the same for the next 2 values. So you take the next 2 values and then you rotate a little bit, and then that represents your next 2 values. And then you do the same, but and this is your m right here. So you do the same for all vectors in your sequence, where this would be m is equal to 0, m is equal to 1, m is equal to 2. So in our case right here, if maybe this vector right here represents enhanced, then you rotate it a very, well, you don't rotate it at all. And say this vector right here represents transformer. Then you would rotate it a very small amount, like right here. And the idea is like we showed above, where you can, like this adds positional information to the word transformer, as opposed to it being as opposed to it just being an unordered set. So it can work with this information, and that's based off the dot product property here, the inner product property, where 2 things are similar to each other if the dot product is well higher, and they leverage that information here. So the dot product isn't only consistent of how close are the queries and the keys in the embedding space, it also consists of the rotation in the embedding space. So I hope this kind of makes sense, where you rotate each part of the vector, or each pair in the vector, by some amount according to where it is in the sequence here. I think this visualization helps, but it's difficult to visualize in d dimensions because there's just so much going on. But yeah, you basically do this at every layer in the transformer right before the queries and the keys are calculated. Let's see if they have that here. Yeah, so your query key transpose, I need to get highlighter. Your query key transpose, which is your attention matrix, is x by w, which I was calling w over here. X by w, or yeah, so you cast this by w, and then you rotate it, and same here. You cast this by w to get your keys, and then you rotate it. So it's the same exact thing as your normal attention matrix, except you rotate all the vectors before you calculate your attention matrix. And that's how the relative positional encodings work. And they're relative because of the dot product property we showed up here. So one other side note is, if you look at this matrix, there's a lot of zeros. It's very sparse. But if you look, but what they do is they just, if you multiply this out here, then you can efficiently represent it here like this, where you just do, it's not a dot product, but if you multiply the dot product out, where it's just a weighted sum by the rotation by the rotation mini matrices of the matrix, then you get a more efficient way to compute this. So it's very fast to compute this. Now, how is this different from the original transformer, where you have the different sine waves? The first thing I mentioned before is you're going to add it at every single layer. So you're going to add it right before the attention, or right before the attention or during the attention actually, for every single layer, because you're multiplying it by the queries and the keys, where absolute is added at the very beginning. So that's one of the biggest differences. Yeah, and then one of the other biggest differences is this is applied kind of. It's a little bit different. So if we look at the, it's kind of similar and it's kind of different. So if we look at the original embeddings, this is an additive property. So it's kind of a superposition of your current signal, which is coming from your data, added to the signal of the positional encodings. While what we have here is multiplicative. So yeah, this is multiplicative, and that perhaps that gives it instead of adding these kind of sines and cosines, it scales it. So that changes the operation that you're doing on the vectors themselves. So those are the two big differences between like absolute and relative, and these rotational positional encodings. Now, I hope that, like I said, I hope that makes sense. It's difficult to kind of, it was difficult for me to kind of visualize, but I hope that made it clear. But now on to the results. So first off, the relative distance relative to where it is in the sequence. So if we start at it not being far at all from, so if we start from, if we start from the word I to the word I, that would be right here. But if we go, as we go further in the sequence relative to each other word, the relative upper bound, which I'm guessing is the relative, like the dot product similarity between the vectors, decreases. So this adds a prior to the model saying the information further away from a word is not as relevant. So if this was the word I, and then love and cats, and then you have a bunch of other words in a paragraph, then you're assuming the word at 250 is a lot less important than the word that's just one position away. And that's what this relative encoding does. And this prior may make sense in some cases, but it may not make sense in other cases. For example, if I had a really long document, then and I needed it to remember information, then it may be difficult for this to remember information if it has to, if some word really far away in the document has to attend to each other, then this upper bound isn't going to allow it to do it that well. At least it'll decrease how large the dot product is going to be, which decreases how much it can attend to that far away word to each other. So that's one thing, but this prior may also be useful to the model, and it doesn't have to learn this prior. I think it more matters depending on like your circumstance for how you're using this. Though they do claim that it consistently achieves. Let me find it. They claim that it gives better performance in general for long. Yeah, right here. Experimental results on various long text classification benchmark datasets show the enhanced transformer with rotary positional embeddings, RoFormer, can give better performance compared to baseline alternatives, and thus demonstrates efficiently. Uh, uh, they basically say that it does well in general on long documents, which I is an interesting property of this, as it shouldn't as the it has this prior not allowing faraway words to attend to each other. So that's an interesting thing that's an interesting claim. But if we go to the actual results, I'm a little. It hasn't convinced me that this works super well. So on the good old blue scores, it does it does a little bit better, but not by a lot. Like it's not a lot. Um, just by 0.2. And if this was the transformer from 2017, then that may be just because of the way we train stuff. Like I said, this paper is from 2022, and we train large language models a lot differently than when they were originally created in 2017. Now, another result, they show that the RoFormer converges faster than BERT, and these, I mean, this is fair, yeah. The way it converges, so yeah, you can kind of see that it does converge faster, and in this case, against the performer without rope embeddings, it definitely converges faster, which is another interesting property. But the results here kind of don't convince me that it works all the time. And like I said earlier, it kind of depends on what task you're doing. I don't know what these tasks are, but I'm guessing that depending on the task, this may work a lot better and it may work a lot worse. Like if you look here, RoFormer does better only half the time uh, compared to default BERT. And I think, I don't know if that is because of how, I don't know if that, like it hasn't convinced me that the reason it does better is because of what they claim it does, because it's so, like, sometimes it does a little bit better and sometimes it doesn't. I haven't seen any results saying that this is better in all cases. Like it's kind of, in some cases it's better and in some cases it's worse. Yeah, they just, and here is another example of that, where you take the original BERT and you take the RoFormer, and it's like it's a little bit better. It's not that much better. Maybe due to noise, and it may be due to just how training is differently from. I think Wobert was 2019, and if you look at the 1024, that like it's a good amount better. It's a whole percentage point better, but that may just because you're putting in a lot more data with the 1024. With the 1024 context. So yeah, like the results here haven't convinced me that it works a lot better than absolute positional encodings, which is just something I want to bring up. It's just something I want to bring up, that I haven't really been convinced that this works a lot better than the default absolute positional encodings, because the results seem to kind of be very similar to each other, and I don't know if it is better or if it's not, or if it is better in some cases and if it's not better in some cases. But since it's used everywhere and it's used in a lot of places, and I would guess it would be a lot better, but I'm not sure. So if you know, please let me know. But yeah, that is the RoFormer. Just wanted to go over this kind of generally before I go into the other paper that I kind of want to talk about, which goes more into how you can extrapolate transformers. So that was RoFormer.